Okay, so we're going to be doing lead code 700 search in a BST, in a binary search tree. You're given the root of a binary search tree, not a binary tree, not an NRA tree, and an integer val. Find the node in the BST that the node's value equals val and return the subtree rooted with that node. If such a node does not exist, return null. Right here you can see 42713 val is 2. So this is a binary search tree. And a binary search tree is one that maintains that all values to the left are smaller than the value at this node, and all values to the right are larger than the value at this point. So what does that mean? That means if we have, for example, 4, 2, 1, 3, and on this side we have 7, we don't need to search each and every node, right? What we need to search is when we're at this point, we check. So we have a value, say our value is 2, right? Actually, let's make it 1. Our value that we're looking for is 1. So we can grab a pointer. This is the non-recursive case. We check, let's say, let's call it current.val, and then current.val less than val, current.val greater than val, right? Actually, let's make our val 3 to make it more interesting. So we have a current pointer starting over here. So we ask ourselves, is current.val equal to the val? Right, our current val is this. Here we'll have current.val equal to val. So we ask ourselves, is current.val equal to val? No, it's not. So what is it? Is it greater than or less than? If it is greater than the val, then that means that the val will be on the left side, so we move to the left side. If it is less than val, then it means our pointer will be moving to the right side. So here, current.val is, let's have our val here. Current.val is greater than, right? Meaning this. So since it's greater than, then that means we need to move to the left side, right? So what's our current val? It's 2. 2 is less than 3. Since 2 is less than 3, then that means we need to go to the right side. So we move here. So our current val is now 3. 3 is equal to 3. So we return this subtree. We simply return cur, right? So that's how you do it. You don't need to use recursion. You don't need to do any of that, because you have a pointer that's iterating through the node. There's a method using recursion, but it will have larger space complexity. I'm still going to show it to you, but it's not worth looking at. So let's write this. So we create we could have our edge case in this case, but we don't really need it. So we create our pointer to the root. So current is equal to root. So while current, in other words, while current is not none, we check if its value is equal to the value we're looking for, to the target. So we'll say if current.val is equal to val, then we simply return that root. Well, we simply return that root. Now we haven't found it, so we decide on which side of the tree to go. So if current.val is greater than val, which is our target, then it means that the value will be on the left side, right? Our target will be on the left side of current node. So that means current is equal to current.left. Then if current, here you can do either else, or you can write again if current.val is less than val, then it means that our target will be on the right side of current node. So current is equal to current.right. So this will terminate once you reach a blank node, right? Once you reach a leaf node and you reach none, it will terminate. It doesn't have to come back or whatever because it's a binary search tree. It automatically eliminates a huge portion of the tree. So then here, if we haven't found it, we simply return none, right? Another thing you could do in order to save time, if root is none, you simply, what did they tell us? Yeah, return none. So you simply return none. So yeah, this is it. Has no attribute. Okay, what's the problem? Okay, we'll just call this else. That could be what's causing the problem. Yeah, so better to just do else here. Better to just do else here, not get any weird errors. Right. So the other solution is recursive, and I wouldn't recommend it because this has worst case n complexity if the tree is badly shaped, but it has space complexity of O1, right? But the other one is a recursive solution. So if root is none, you simply return none. Then if root.val is equivalent to val, you simply return root, right? Then if root.val is less than val, it means that it will be on our right hand side, right? Because our current node, that means the val will be in the right subtree. So return self.search bst root.write val. Else means root.val is greater than val, which means it will be in the left subtree, right? So you do this, place it here, but left, right? So this should give you none. Right? This should give you the result. Yep, and it works. But I would recommend the previous solution, which was this one. This is the best solution. This is the best solution. Okay, so yes, that is the solution to this problem. Thank you and bye.